Hello everyone, my name is Brian Fisher. I'm a professor of interactive arts and technology at Simon Fraser University. I also have multiple research affiliations at the University of BC and a Brain Research Institute, Computer Science, and an Interdisciplinary Institute. I was invited to speak because I'm a general chair for IEEE VIS 2019 that will be held next October in Vancouver, BC. VIS is a collection of conferences that co-locate. It's centered around three main conferences. VIS is an acronym. VIS stands for Visual Analytics, Information Visualization, and Scientific Visualization, the three main conferences. If you submit to the conference, you can choose one of those, or you can submit to the event, and the paper's chairs will decide which one is the best fit. Full papers at VIS become journal articles in IEEE Transactions in Visualization and Computer Graphics. In addition to the three main conferences, there are multiple events, even an art show. There's VisX Vision, a workshop that you're at today, has a corresponding workshop at our conference. There's also Believe, which looks at ways of evaluating human interaction with these visualization interfaces. A doctoral colloquium for people whose doctorate their dissertation project will be something that deals with visualization, and many other events. In addition to chairing VIS this year, I've been involved for many years in administering the conference. So VIS, the whole event, is organized by an executive committee that I sit on. The VAST conference has a steering committee, and I've been on that steering committee. And also, because I've been involved in the field for over 20 years, I'm part of a group called the Visualization Pioneers Group. In the applications of visualization, I've served on the leadership board of the U.S. National Network of Centers of Excellence in Visualization, Vaccine, and I contributed to the research agenda document that gave rise to the field and gave rise to the support for that Center of Excellence. Now, before I was a visualization researcher, I was a vision scientist. Here are some pictures from a number of Sarasota VSS events. I went to VSS for over a decade. I did my doctorate with Bruce Bridgman, who you'll see in the center panel on the right. When I worked with Bruce, I worked on two visual systems, saccadic suppression and displacement. My doctoral dissertation was in integration of vision with hearing and multimodal event perception. From there, I went to a postdoc with a fellow on the left, Zenon Polishin at the University of Western Ontario, where I worked on multiple object tracking, visual search, and related areas. I'm going to step back and take a look at the history of VIS to give you an idea how the conference came about. VIS began really in a meeting in the National Science Foundation. People had been making graphical representations of scientific data for many years, of course, and computer graphics was becoming increasingly important. So that group met and they came up with a report that was published as a special issue of the Computer Graphics Journal, and they came up with the idea of having an annual conference, which became in 1990. Their concerns were really with the computer graphics and data processing aspects. In the early days, these were very computationally challenging. They wanted to take digital data that came in from analog to digital converters, from things like CAT scans and fMRIs. They wanted to map these in space in such a way that they can align multiple data sources. There were a lot of technical challenges. As research in this area progressed, people became interested in using computer graphics to display other kinds of data for other kinds of tasks. And so the field of information visualization was born. The first IEEE Information Visualization Conference was held in 1995 with a focus on the design of representations of information that could come from arbitrary sources, not necessarily scientific data. The keynote for that conference was done by a cognitive scientist, Stuart Card, and it was entitled Information Visualization, Wings for the Mind. And Dr. Card reminded them that the purpose of computer graphics was to support humans to do complex cognitive tasks. And when you design these visualizations, you need to be thinking about the human operating characteristic. Computer visualization can increase the memory and processing resources that a person has to do a difficult cognitive task. You can reduce the search for information by using visual representations to enhance the detection of patterns. So you needed to know something about how we see patterns. We have perceptual inferences that we make about visual representations, what Irv Rock called the logic of perception or visual intelligence more recently. You need to know about perceptual attention because you can use that so that they can monitor channels to see if there's been a change. And you should support the manipulation of information. So in Stuart Card's mind, information visualization was something that needed to be integrated with perceptual and cognitive sciences. Well, the field rolled on for many years. Here is a periodic table of different visualization methods, many of which were developed and presented at IEEE Information Visualization and Scientific Visualization. I'll pull a few examples from these tables. On the left, you see scientific visualization examples, a spectrogram, a visual representation of sound, often speech, and parallel coordinates, a way of taking a high-dimensional space and reducing it to a two-dimensional representation. On the right, you see information visualization examples, a semantic network in which the relationship between the nodes is determined by their semantics, and a Sankey diagram which looks at how different sources of energy can be used for different purposes. The thing that becomes immediately apparent is that these are not bar graphs, where a bigger bar means more. Understanding these representations is something that requires perceptual expertise as well as conceptual knowledge and procedural expertise. Effectively, you read these representations almost like reading text. Your eyes move across them as you begin to make different inferences and you pursue different cognitive tasks. So this is a very complex kind of HCI, if you will. Based upon these concerns, a number of us began to wonder whether we needed more cognitive science and more involvement in application areas. One of the leaders in this was Bill Lawrenson, a computer graphics researcher, and he wrote a paper in a 2004 NSF NIH workshop on visualization, in which he asked whether visualization can survive without customers. And so this was a real challenge for the field. He said, visualization is not a solution, but it's a critical part of many applications. We in the community don't have the application domain knowledge we need. As a result, visualization has become a commodity and we're not having an impact in applications. People use Microsoft Excel, they don't use the visualizations we create. If you look at how visualization is being used in different application areas, you will see some of the complexities. So these are all areas that we've worked on in my lab. In the upper left and the lower right, we have health visualizations. These may be simple representations, but they're presented in a dashboard. In the upper left, we're doing work on child injuries, and in the lower right, we're doing work on personalized multi-omic medicine. Someone, an expert, has to read these representations and understand them. In the upper right, we have some work we did in collaboration with colleagues at Stuttgart, and we're doing eye movement analysis of how people work in this complex data space. On the lower left, we have some work we did with Boeing on computer-aided design presented in 3D environments, a cave environment. So how do we make visualization more effective? Well, this is something that requires us to understand how people reason in these applications. Perceptual inference as well as cognitive task analysis. This discussion was ongoing for some time. It came to a head at a party at Zenon Polishin's house for myself, in which I was discussing with a computer scientist that we needed to get more vision science and more cognitive science into visualization. We wrote a grant proposal, which was successful, a cognitive basis for the design of intelligent user interfaces to complex systems. That funded me as a postdoc to shuttle between Polishin's group in London, Ontario, and computer graphics labs at Simon Fraser University and the University of BC. When I was in Ontario, I did research with Polishin's group on visual cognition, and when I was in BC, I did work on graphical application projects, trying to put that knowledge into the computer graphics that they were creating. At that point, I was invited to join a group that was setting up a research agenda for the United States to try to have a science of analytical reasoning, human reasoning, as it's facilitated by these complex interactive visual interfaces. This agenda document is still available. Proposed that visual analytics would be this science of analytical reasoning. It would enable users to develop insights. We would look at visual representations that take advantage of the perceptual inference. We would look at data representations and transformations and techniques that would support its use in organizations. From a perspective of a vision researcher, you look at computer scientists, the computer graphics researchers, and you see that they have access to a lot of funding and some really nice display technologies. They have students who code really well and can do the complex computer graphics that are often a challenge for vision researchers. They have new phenomena that roll out of these complex environments they create and the challenging tasks that people perform by using them. On the other side, vision science has something to offer the computer scientists as well. They understand visual phenomenon. We have theories that can explain them. You look at these interfaces and you see places in which the theories that you know could be applied. And they have students who know how to design and run experiments really well. And my job was to be between the computer scientists in Vancouver and the vision scientists in Ontario, and to be a sort of a connector to try to bridge these areas. I'll just briefly give an example of some work that we did. This is some work with an air traffic control display that we were hired by Hughes Raytheon Labs to look at the proposed next-gen air traffic control. When we looked at the display, we realized that they were taking a fish tank VR space, a three-dimensional space that would float in front of the user, and they were proposing to rotate that space as the aircraft moved within it. Coming from Pollution's lab, I saw multiple object tracking in a display that itself was moving. I thought, do we know how to do this? Well, no one had done that research, so this is our lab mascot. We would do it. And we took a Pollution in Storm style display. You're asked to track the points that are surrounded by the red circles. And then we ask whether this is your item or not as soon as it finishes its movement. Well, we ran the parameters on this, different seed speeds, different object speeds, different number of objects, and you find that the scene speed doesn't seem to affect performance. This was interesting enough to give us a Journal of Experimental Psychology paper. So when I look at the Visualization Conference, you see some trends that seem to be gaining momentum. We're seeing more and more vision science and cognitive psychology papers. These papers were something that were initially peripheral to the field. They're now becoming much more central. They're winning Best Paper awards. We're seeing a lot of outreach to applications, the groups that rely on decisions that are made with these environments. The key thing is in bringing in the applications, the people who need to have good decisions made with these environments, we find that they want scientific validation. They look at these visualizations and they want to know that people can use those visualizations in cognitive tasks. And that creates opportunities for basic research. A lot of our basic research funding has come from places like Boeing, like Nissan, like HRL, and with General Motors Research. Viz really needs these submissions and qualified reviewers to review them. There's also a movement in the Viz community to restructure, and that may be useful for us in the future. There's inclusivity and different applications groups that are getting a lot of interest, and these committees are going to influence the structure of the conference. The revised initiative is worth a particular attention. This proposes that we move from those 3 conferences to a single conference that will have different areas. And this group is trying to define what those areas may be. If you're interested, you can click on this URL and you'll see the public documents and you can weigh in on this discussion. If this initiative succeeds, I hope that we'll see an increase in vision science at VSS, particular at Viz, perhaps as a whole area in and of itself. If this happens, we'll have an even greater need for your submission, but especially a need for you to come to review papers from your perspective. When someone submits a paper that makes claims about human vision, it should be reviewed by someone who knows the theory and methods that give rise to the science of human vision. I'll conclude with a mention of the students and postdocs that contributed to these research that I mentioned only briefly here. Thank you very much for your time, and I hope to see you at VIS next year.